previous classes, we were discussing about the partial derivatives of functions of several variables. Today, we're going to discuss about kind of applications of these partial derivatives or further uses of these partial derivatives in the field of calculus itself. The first one is about directional derivatives. Directional derivatives. We are familiar with the word derivatives, and what makes it special? What makes it special when we add directional? So how does this direction involves with the derivative? That's the first question. Okay, so what was actually derivative? Suppose we have a function f of xy. Right, we have a function f of xy. And what did we mean by fx and fy, or simply the partial derivatives with respect to x and y? This was identified as the rate of change of if we had our function as z of f of xy, fx was identified as the rate of change of z in the direction of x or with respect to x, right? Similarly, fy was identified as the rate of change of z in the direction of y, right? So let's go to the domain set. You remember the word domain, right? See, here we have a function of two variables. So the domain appears to be a plane, right? So this is the x direction, and this gives the y direction, the positive x and the negative x and negative y and positive y, right? Suppose we are trying to find the derivative at origin, say origin, at the partial derivatives at origin, or not simply derivative at origin. Fx actually gives the rate of change of z in the x direction. Right? Similarly, fy gives the rate of change in the y direction. Is that the only possible direction? These are the only possible directions? Obviously not. We can approach from this side, or any side. Right? These are all possible directions. In fact, this is not the actual method to do this. If it is possible, visualize the graph of a real valued function of two variables. It will be a surface in 3 dimensions, and on that surface, fx and fy gives the rate of change of z in x and y direction. But as we have seen now, there are many more directions in which the variables can change and reflect in the function, right? So we think about a possible generalization of this partial derivative concept, and there we reach directional derivative. And once we define and explain directional derivative, we will try to identify the partial derivatives as a special case of directional derivative. Right. So let's formally define the directional derivative. Okay. So before moving to directional derivative, remember these two things. Dou f by dou x and dou f by dou y actually gives the rate of change of f or z, whatever, in the x and y direction, and we don't have any need, or we are not actually confined to only two dimensions, two directions. We can think about more and more directions, and that give rise to directional derivative. And for the easiness to define and explain directional derivative, let's first define gradient of a function. Gradient of a function. Suppose we have a scalar function of two variables, say f, x, y. the gradient of f of xy denoted as grad f, we call this grad f. You might be familiar with this operator. Grad f equal to dou by dou x of f of xy, or dou f by dou x simply. See, this is a function of xy again. So grad f of xy is equal to dou by dou x of f of xy I plus dou by dou x of f of xy j, where this I and j are unit vectors in the directions of x and y maybe. Okay, so first we had a scalar function of two variables, and from that we evolved or we obtained a vector valued function. See, this function is not just a scalar function, this function returns a vector. This has two components, right? This actually returns a vector. So this is a vector valued function, and this is called the gradient of f. Right. So this gradient operator, dou f, is actually nothing but dou by dou x I plus dou by dou y. Oh, see, this is y, this is y. Dou by dou y j. Or simply the operator. If it is f, you can simply plug f here. If it is some g, you can simply plug g here. Right. So this is the gradient operator, and we apply this gradient operator to a function to get a vector valued function from a scalar function. Right. So remember this expression to find the gradient of a function. This gradient has got wide ranges of application in calculus, and now we can use this gradient to define directional derivatives. Prior to that, let's see an example of gradient. Consider the function. See, all these things we explain in this session is actually applicable to any number of variables. These are not actually confined to the functions of two variables. Right. For the sake of easiness and convenience, we consider two variable functions, and you can actually think about possibilities of more and more variables and simply extend these results to them. Right. So suppose we have a three variable function, say f of xyz equal to xy squared plus 3x squared minus z cube. Find the gradient of f of xyz. See, for a three variable case, we write the grad function or gradient operator as dou by dou x I plus dou by dou yj plus the obvious extension dou by dou z of dou z k, dou by dou z k. Right, well, these are unit vectors in the xyz direction or the mutually perpendicular direction, coordinate axis. Okay, so let's find the gradient of this function. So if f of xyz equal to x squared plus 3x squared minus z cube, dad f equal to dou f by dou x. See, these are observed as suppose the question is to find the gradient of f at, say, a point 2 minus 1, 4. Right, let it be there. So let's find the gradient at xy in general. Dou f by dou x I plus dou f by dou y j plus dou f by dou z k. So what is dou f by dou x? The partial derivative of f of xyz with respect to x. You know how to differentiate it. We keep y and z as constant and differentiate with respect to x. This will give y square plus 6x minus 0. So that's fine. Into I plus dou f by dou y. We keep x and z as constants and differentiate with respect to y. So 2xy is fine. Both other terms are actually independent of y, and the derivative will be 0 for that reason. J plus dou f by dou z. We keep x and y as constant and differentiate with respect to z. This gives 0, 0 and minus 3z square k. Right. So this is the gradient of f at xy, but we are actually asked to find the gradient of xyz, xyz, xyz. So we are actually asked to find the derivative at 2 minus 1, 4. Now simply plug these values into this equation. 2 for x and minus 1 for y and 4 for z. Right. So that will be minus 1 square will be 1 plus 6 into 2 will be 12i plus 2 into x into y. 2 into minus 1 is minus 2. So 2 into minus 2 is minus 4. Minus 4. Minus 4j minus 3 into z is 4. Z square is 16. 16 into 3. 48. 48k. So this is nothing but 13i minus 4j minus 48k. Right. So this is the gradient of f at 2, minus 1, 4. So this is how we practically evaluate the gradient of a function. So remember, gradient is not just a simple function, but it's a vector valued function. It's a vector valued function. Right. Now we can use this directional derivative, gradient to evaluate the directional derivative of a function. Right. Suppose, let's formally define the directional derivative first. Suppose we have a function f. Right. Say it's a two variable function. See, you can simply extend this to 3 or higher variable cases. Suppose we have a function f of xy. The directional derivative, see, directional derivative itself says something about the direction. So we need a direction to find the derivative here. Right? We are actually expressing derivative in a specific direction. So the direction should be specified. So the derivative of f of xy in the direction of direction is always being given in the form of unit vectors. In the direction of say unit vector say what, cos theta I plus sin theta j. This is a conventional form of unit vectors, right? Will this be a unit vector? What about the modulus? Will be root of cos square theta plus sin square theta? Will be root of 1, which is 1. Right. So the directional derivative of f of xy in the direction of u equal to cos theta I plus sin theta j is given as a limit du fxy equal to. See, this means the directional derivative of f of xy in the direction of u. Directional derivative of f of xy in the direction of u as limit h tends to 0 f of x plus h cos theta y plus h sin theta minus f of xy all divided by h. Right. Provided the limit exists. We have seen that the limit does not, need not exist everywhere. So this definition stands valid when the limit exists. So let's have a relook at the definition. The directional derivative of the function f of xy in the direction of u at xy is given as limit h tends to 0 f of x plus h cos theta y plus h sin theta minus xy. Okay. We have just mentioned that once we define the directional derivative, we will make an attempt to find the partial derivatives dou f by dou x and dou f by dou y as a special case of directional derivative. Let's see how does it work. What is the unit? Suppose we have two directions, that of x and y, which are the directions of coordinate axis. So what is the directional derivative of or the unit vector in the direction of x, and what is the unit vector in the direction of y? Or we don't even need that. Let's analyze two special cases where theta equal to 0 and theta equal to pi by 2. Right. Before explaining anything about theta, we discussed about a unit vector u equal to say cos theta plus cos theta I plus sin theta j. Right. What is theta here? Theta is the angle made by this unit vector with the positive direction of x-axis. Suppose this is our axial system and we have a unit vector here. This is theta. Right. If that vector is here, theta is 0. So the unit vector in the direction of x-axis is the unit vector making an angle of 0 degrees or 0 radians with positive x-axis. And what is the unit vector in the direction of y-axis? It is the unit vector which makes an angle of pi by 2 radians or 90 degrees with respect with the positive direction of x-axis. Alright. So theta equal to 0 actually gives the unit vector in the direction of x-axis, and theta equal to pi by 2 actually gives the unit vector in the direction of y-axis. So we expect that the directional derivative in this direction will give us dou f by dou x, and the directional derivative in this direction, theta equal to pi by 2, which is the direction of y-axis, will give us dou f by dou y. Let's check it out whether we can obtain that. So if theta equal to 0, cos theta is 1 and sin theta is 0. So let's plug theta equal to 0 in this equation. We'll get du f at xy equal to limit h tends to 0 f of, see, if we plug 0 in this theta equal to 0, we'll have x plus h into cos 0 is 1, so will be x plus h, comma, y plus h into sin 0 is 0, so y plus 0 will be y, minus f of xy divided by h. This is obviously the expression for dou f by dou x. I hope you remember, which we have expressed in the previous classes and explained. So this actually gives the expression for dou f by dou x. So the directional derivative of f in the direction of the unit vector having a angle of 0 degree with the positive x-axis, or in the direction of x-axis itself, is dou f by dou x. Similarly, let's evaluate the case where theta equal to pi by 2. Limit h goes to 0 f of, when we plug theta equal to pi by 2, cos pi by 2 is 0 and sin pi by 2 is 1. So f of x plus h into 0, which will be f of x, y plus h into sin pi by 2, which is 1, so y plus h minus, doesn't make any changes, f of xy divided by h. This is nothing but the expression for partial derivative with respect to y, or dou f by dou y. So the directional derivative of f in the direction of the unit vector making an angle of pi by 2 with the positive x-axis, or in the direction of y-axis, gives the partial derivative dou f by dou y. Okay, so this is how we identify the partial derivative as special cases of directional derivatives. Right. Alright. So even we have, when we discussed about derivatives, we had a limit expression. Right. Limit x tends to 0, some f of x plus h minus f of x divided by h kind of thing. But we never used this expression to find the derivatives. We had other techniques, our own techniques, to find the derivative of a function in the practical sense. In the same way, the directional derivatives are not practically found using that limit thing. Somewhere, in some special cases, we may use that limit formula or expression or the formal definition. But in almost all other practical cases, we have another technique to find the directional derivative. Let's state and prove a theorem regarding that. The theorem states that if z equal to f of xy is a differentiable function, see, you can extend these to 3 or 4 variable functions, doesn't matter. For the sake of convenience, we consider only a 2 variable function for now. A differentiable function of say x and y, and let u equal to cos theta I plus sin theta j. See, our unit vector has two components here for the reason that we are thinking about a two variable function. But when you have a three variable function, the unit vector must also be expressed as a vector having three components. Right? There will be a k component. Alright. Or a z component maybe. So equal to cos theta plus I plus sin theta j be a unit vector. Then the directional derivative of f in the direction of u at xy, this gives the meaning that the directional derivative of f in the direction of u at xy can also be defined as grad f or gradient of f. See, instead of saying literally gradient of f, we may sometimes use it as grad f. Grad f just means gradient of f. So grad f dot u, but this is the usual dot product of vectors. Grad f is a vector function. We have seen that u is again a vector, so we know how to take the dot product of two vectors. Right. So instead of using that current limit expression, we can simply use this simple formula to find the directional derivative of a function in a specific direction. Right. This theorem has to be proved. We'll prove this theorem. Proof. So what do we have? We have a function f of xy, so is that equal to f of xy or whatever, and a vector or unit vector cos theta I plus sin theta j. Okay. For now, let's fix x, y and theta. Let's fix x, y and theta and define a new function of t as g of t is equal to f of x plus t cos theta y plus t sin theta. If we fix x and theta, this is actually a function of one variable t, right? If we fix x, y and theta, the only thing changing here is t. So this happens to be a single variable function, right? If this is a single variable function, we can think about the usual derivative, right? Now our strategy is to find g dash of 0, the derivative of g with respect to t at 0, but in two different ways. First, we will use the formal definition using limits, and then we make use of the chain rule which you have learned. And we will get two different expressions from this, and we will equate them to reach at our conclusion, right? So let's first use the limit definition of derivatives. So g dash of t is actually given as limit. See, let's directly apply g dash of 0, right? It's that simple. G dash of 0 is limit h tends to 0, g of 0 plus h. See, if we had t here, it will be g of t plus h here, minus g of 0 divided by h. This is how we find the derivative at 0, right? This is equal to limit h tends to 0. What is g of 0 plus h? Or this is nothing but h now. 0 plus h is h. What is g of h? If g of t is this, g of h can be easily found as simply by replacing t by h. So limit x tends to 0, f of x plus h cos theta y plus h sin theta minus, what is g of 0? If we plug 0 in the place of t, we'll have f of x plus 0 y plus 0, which is nothing but f of xy divided by h. Right. What is this? This is exactly how we defined the directional derivative of the function in the direction of cos theta I plus sin theta j. a little ago. Right. So this is nothing but the directional derivative of f in the direction of u at xy. Right. Copy this and we call this as a. Okay. So when we found g dash of 0, we got the directional derivative. Okay. Now let's clear this off. Now we can make use of chain rule to find the directional derivative of g with respect to 0. So let's find g dash of t. F is a function of two variables here, right? We have a first variable and we have a second variable, and conventionally we call the first variable as x and second variable as y. Don't get confused with these two x's here. These slightly have a change in their meanings. For now, for the sake of our convenience in the notations, I consider this whole term as y and this whole term as x and this whole term as y, accepting the convention that the first variable is considered to be x and the second variable is considered to be y. If it is the case, we can simply write the partial derivative of f with respect to the first variable as fx and fy, which will in turn get aligned with our previous expressions and the upcoming expressions including partial derivatives. Right. So it doesn't get confused with these two x's. So g dash of t equal to, how to use the chain rule. We have seen the chain rule for partial derivatives. So g dash of t can be found as dou f by dou x of f of x plus t cos theta y plus t sin theta into, again the first variable x is a function of t, x plus t cos theta. So if you differentiate it with respect to t, you will get a cos theta here, cos theta, plus dou f by dou y of x plus t cos theta y plus t sin theta into, again the second variable is a function of t. If you differentiate y plus t sin theta with respect to t, you will get a sin theta. Right. This is what we get. Observe this. Can I rewrite this as dou f by dou x? See, I don't write x plus t cos theta thing here. Oh, before that, we were asked to actually trying to find the g dash of 0, right? Okay, so what is g dash of 0? Plug t equal to 0 everywhere, which will be dou f by dou x at, or x plus 0, y plus 0 into cos theta plus dou f by y, x plus 0 and y plus 0 into sin theta. Right. So we got dou f by dou x, dou f of xy by dou x cos theta plus dou f of xy by dou y sin theta. Okay, so can we think this about as a dot product? See, we have a term here multiplied with multiplied with another term. The same for the second term, right? Consider this can be expressed as dou f by dou x. I don't write x and y again. You know, this is a function of x and y, right? Dou f by dou x plus dou f by dou y. I consider these to be vectors. Dou f by dou x I plus dou f by dou y j, dotted with cos theta I plus sin theta j. How do we find the dot product? The first term into first term plus second term into second term. So the first term into first term is dou f by dou x into cos theta plus dou f by dou y into sin theta. This is exactly what appears here. Okay, what is this? Dou f by dou x I plus dou f by dou y j is nothing but the gradient of f, the grad of into, this is actually the unit vector we were given to find the directional derivative in the direction of. So this is u. Right, I call this b. You remember the a we got, which was du f of xy, and now we got dou f. See, actually these are functions of x and y. grad f dot u. But we obtain these two things from the same item g dash of 0. So we got the same, we started from the same scratch g dash of 0 and ended up these two. So obviously if the left hand side is equal, the RHSS has to be equal. From that idea, we conclude that du fxy equal to grad f of xy dot u. So the directional derivative can be found as the dot product of gradient and the unit vector. Alright, so this is how we practically evaluate the directional derivative. Let's see an example of this. Consider the function f of xy, right, equal to 2x square y cube plus 6xy. It's just a simple case of two variable function at 1 1 in the direction. Find the directional derivative of f of xy equal to 2x square y cube plus 6xy at 1 1 in the direction of a unit vector which makes an angle of pi by 6 radians. So theta equal to pi by 6, theta equal to pi by 6 radians with positive x-axis. Okay, so we can simply plug all this information to our formula. So directional derivative at xy can be found using grad f dot u. So let's first found the gradient of f. So gradient means dou f by dou x I plus dou f by dou y j. This is equal to, what is dou f by dou x from this? Keep y as constant, differentiate with respect to x will give. So this will be 4xy cube plus dou f by dou y at j. Oh, yeah, no. 4x cube y plus 6y I. Right, this is dou f by dou x plus dou f by dou y. We keep x as a constant and differentiate with respect to y. Will be 6x square y square plus 6x, right, into j. So this is grad f. What is this? What is the value of grad f at 1 1? We are asked to find the gradient at 1. Sorry, the directional derivative at 1 1. So we simply simplify these things here. Will be 4 plus 6i plus see, we plug everything as 1, x and y as 1, plus 6 plus 6 12 j. So this is 10i plus 12j, right? So I shall clear this, So the theta was actually pi by 6. The unit vector was given as u equal to cos theta I plus sin theta j, and we know what is theta. So this is actually cos of pi by 6 I plus sin of pi by 6 j. That is nothing but cos pi by 6 is root 3 by 2 I plus sin pi by 6 is 1 by 2 j. So we got grad f and we got the unit vector. Now we can take the dot product as grad of dot u equal to 10i plus 12j dot root 3 by 2 I plus 1 by 2 j. Okay, so let's clear this off. This is equal to, so how do we take the dot product? First term into first term. This is 10 times root 3 by 2 plus 12 times 1 by 2. This means root 3 by 5 plus 6. Right. Oh, not root 3 by 5. 5 times root 3, right. 2 and 10 will be cancelled out. So this is 5 root 3 5 root 3 plus 6. So this actually gives the directional derivative of directional derivative of f in the direction of u at 1 1, right, not just as xy. This gives the specific directional derivative in the direction of u. U was the unit vector making an angle of pi by 6 with the positive x-axis, and directional derivative was evaluated at 1 1. Okay, so this gives a practical example of evaluating the directional derivative of a function as a dot product of gradient and the unit vector.